What if I told you there are places in the universe where not one, not two, but 6 suns rise and set in a single sky? Imagine a cosmic dance so intricate, so chaotic, that it defies everything we thought we knew about how stars form and behave. Sextuple star systems, those rare, mind-bending celestial wonders where 6 stars orbit one another, are more than just astronomical oddities. They're cosmic puzzles that challenge our understanding of gravity, stability, and the very fabric of space itself. These systems are Chinese letter, so impossibly balanced that spotting one feels like uncovering a secret the universe never meant for us to find. For centuries, we've gazed at the night sky assuming stars like our sun prefer solitude or, at most, the company of a single partner. But sextuple systems shatter that illusion. They're gravitational roller coasters where stars whirl around each other in patterns so complex, even the most advanced simulations struggle to predict their movements. Picture this, a place where multiple suns cast overlapping shadows, where day and night blur into a kaleidoscope of light and darkness, and where the laws of physics are pushed to their absolute limits. Astronomers have spent decades unraveling their secrets, and what they've discovered is stranger than fiction tales of stars stealing material from one another, of bizarre eclipses that last for years, and of orbits so tight they shouldn't exist. This isn't just about counting stars, it's about confronting the unexpected. Every new observation of these systems reveals something that shouldn't be possible, something that forces us to rewrite the rules. Why do these cosmic families exist? How do they avoid tearing themselves apart? And what can their extreme environments teach us about the birth and death of stars across the universe? Buckle up, because we're about to dive into 30 of the most astonishing discoveries from these stellar marvels. Each one a reminder that the universe is far wilder, far more inventive than we ever dared to dream. Among the countless stars scattered across the cosmos, one system stands out as the first confirmed cosmic sextet HD 98800. Discovered in the 1990s, this gravitational masterpiece sent shockwaves through the astronomy community, upending assumptions about how multiple star systems could exist. Nestled within the TW Hydra Association, a young stellar nursery roughly 150 light-years away, HD 98800 isn't just 6 stars orbiting haphazardly. It's 2 separate triple systems locked in an intricate waltz, each trio dancing around a shared center of mass before pirouetting around one another in a grander, slower embrace. At first glance, the arrangement seems impossible, a celestial Jenga tower defying collapse. The inner stars whirl around each other in tight orbits, some so close they could fit within our solar system's asteroid belt, while the outer pairs swing wide, tracing lazy arcs over decades. Gravitational forces here don't just push and pull, they negotiate. One misstep, one unstable shift, and the entire system could unravel. Yet against all odds, HD 98800 persists, a testament to the delicate balance of cosmic mechanics. What makes this discovery even more astonishing is its youth. Unlike ancient star systems that have settled into predictable rhythms, HD 98800 is a stellar toddler, offering astronomers a rare glimpse into how such complex systems emerge. Infrared observations revealed thick disks of dust and gas swirling around some of its stars' potential nurseries for future planets. But how could worlds form here where gravitational tides from multiple suns would constantly stretch and warp planetary orbits? The existence of HD 98800 forces us to reconsider not just how stars relate to one another, but how entire solar systems might arise in the chaos of such extreme environments. When astronomers first pieced together its 6-star puzzle, the discovery didn't just add to the catalogue of exotic celestial objects, it rewrote the rules. Before HD 98800, conventional wisdom suggested that systems with more than 3 stars were too unstable to last. Yet here was nature, showing us a configuration so elaborate it seemed almost artistic. The system's very existence whispers a tantalizing question. If this is possible, what other stellar surprises are waiting in the dark? Deep in the constellation of Ursa Major lies a cosmic hall of mirrors, TSE 168789840, a sextuple star system that plays tricks with light and gravity. Unlike HD 908800's broad orbital dance, this system gives astronomers a front-row seat to something extraordinary. Stars that cross in front of one another from our viewpoint, creating a celestial light show of eclipses. These aren't the fleeting shadows we see in our solar system. Imagine 6 suns weaving in and out of alignment, their orbits so precisely angled toward Earth that they dim and brighten like clockwork, revealing secrets no telescope could uncover otherwise. What makes TSE 168789840 so valuable is its gift of precision. Every time one star passes in front of another, it acts like a natural scale, allowing astronomers to measure stellar masses with uncanny accuracy. The timing of these eclipses, some lasting hours, others stretching across days, paints a portrait of orbits tangled in gravitational chaos. One pair might circle each other every 1.6 days, while another duo takes 20 years to complete a single loop. These overlapping rhythms create a symphony of motion so complex, it feels less like a system and more like a stellar mosh pit. But the real shock came when researchers realized this wasn't just a random celestial free-for-all. The eclipses exposed layers of gravitational interference, where one pair's orbit gets yanked unpredictably by the others, creating wobbles that defy simple models. In most star systems, gravity follows orderly rules, but here, it's as if the stars are playing a high-stakes game of tug-of-war, with momentum constantly stolen and traded. The most baffling part, how often these eclipses happen. With 6 stars in the mix, you'd expect moments of alignment to be rare. Yet TSE 168789840 serves up eclipses like cosmic clockwork, some so frequent they've allowed scientists to track minute changes in orbits over just a few years. This isn't just a static snapshot, it's a live feed of stellar evolution, showing how these stars nudge and reshape each other's paths in real time. What these eclipses reveal goes beyond textbook astronomy. They've uncovered stars so close together that their atmospheres bleed into one another, trading material like partners in a ghostly waltz. In one case, a hotter star was caught siphoning gas from its cooler companion, leaving a glowing bridge of superheated plasma between them. These aren't just stars coexisting, they're stars rewriting each other's stories, proving that even in the vastness of space, no sun is truly an island. For planet hunters, TSE 168789840 poses an exhilarating challenge. Could worlds exist in this gravitational storm? If so, their skies would defy imagination, a canvas where multiple suns rise in staggered succession, casting ever-shifting shadows. But survival here would require orbiting so far out that years might pass between sunrises, or clinging so close to one star that the others become distant specks. Either way, this system forces us to rethink the very definition of habitability, proving that the universe's rulebook is far from finished. Nu Scorpii isn't just a sextuple star system, it's a cosmic crime scene. While most multiple star systems form from the same swirling cloud of gas and dust, making them stellar siblings with similar ages and compositions, Nu Scorpii defies the rules. Here, stars of wildly different origins and life stages orbit one another in a gravitational tango, as if the universe stitched together a Frankenstein monster from spare celestial parts. Astronomers studying this system found young, blazing hot stars locked in orbit with ancient, cooler ones, their mismatched chemistries betraying a violent past. Some show traces of lithium, an element usually burned away in a star's infancy, while others bear scars of helium-rich atmospheres, evidence of turbulent encounters that reshaped their very cores. This chaos points to a history far more dramatic than peaceful formation. Unlike HD 98800, where stars move in coordinated trios, Nu Scorpii's members seem like strangers forced into reluctant partnership. The leading theory, a series of cosmic smash and grabs. Picture this: a wandering star drifts too close to a tight binary pair, only to be captured by their gravity. Later, another interloper crashes the party, triggering a chain reaction of chaotic encounters. Over time, these gravitational hijinks could have reshuffled the system into its current unstable harmony. Infrared observations revealed dusty debris fields around some stars, likely the fallout from these violent mergers, where stellar atmospheres were torn apart and remixed like ingredients in a blender. The real puzzle is how Nu Scorpii stars haven't torn each other apart. Most models predict such a mixed bag of ages and compositions would lead to catastrophic ejections, leaving only a few survivors. Yet against all odds, this system holds together, its stars tracing elliptical orbits that swing dizzyingly close before recoiling to safer distances. These extreme paths suggest the stars are locked in a gravitational tug-of-war, constantly stealing and trading momentum in a high-stakes game of orbital brinkmanship. For theorists, Nu Scorpii is a nightmare and a revelation. It challenges the neat narrative that stars in a system must share a common origin, forcing astronomers to reconsider how often stellar kidnappings might occur in dense star-forming regions. If systems like this can exist, then our galaxy might be teeming with hybrid stellar families, each one a patchwork of stolen stars, forced alliances, and survivors of ancient collisions. Nu Scorpii doesn't just defy expectations, it demands we rewrite the story of how stars live, die, and sometimes unwillingly adopt one another. Some stars don't just dance, they sprint. In the Sextuple system HD 139691, the cosmos serves up a spectacle of speed so extreme, it redefines what we thought possible for stellar orbits. Here, two of the system's stars whirl around each other in a blistering embrace, completing a full lap in just under 2 days. That's faster than some planets orbit their suns, a velocity so dizzying it warps the stars themselves into egg-shaped monstrosities, stretched by tidal forces that could rip a lesser system apart. The closer two stars orbit, the more gravity distorts them. But HD 139691 takes this to a terrifying extreme. Imagine a star so close to its partner that its surface bulges outward, not just slightly but grotesquely, like a balloon squeezed between two hands. These tidal forces don't just alter shapes, they rewrite stellar fates. Gas from the swollen star's outer layers gets tugged toward its companion, forming a swirling bridge of superheated plasma. Sometimes that bridge snaps, unleashing catastrophic flares that outshine both stars combined. Astronomers have caught these eruptions in action, bursts of energy so violent they mimic the death throes of much larger stars. Yet the real surprise isn't the flares themselves, but what triggers them. In comma binary systems, mass transfer tends to be steady, like a siphon. Here, it's a tempest. The star's breakneck orbits create whirlpools of magnetic chaos, twisting and knotting their atmospheres until they snap like overstretched rubber bands. Each eruption leaves its mark, chemical fingerprints revealing how material has been stolen, mixed, and flung into space. Over millennia, this relentless theft could strip one star entirely, leaving behind a ghostly core while its partner swells into a bloated, reanimated version of itself. What makes HD 139691 truly baffling is how this high-speed pair coexists with 4 other, slower-moving stars. The system shouldn't be stable. At such speeds, the inner duo's gravity should act like a cosmic wrecking ball, flinging their outer siblings into the void. Instead, the system persists a delicate balancing act where the stars' combined gravity forms an invisible net, keeping the chaos contained. It's as if the universe threaded a needle, allowing 6 stars to coexist where even 2 should spell disaster. For astronomers, this system is a natural laboratory for extreme physics. The flares offer glimpses into how stars exchange mass under conditions never replicated on Earth. The orbits precise enough to set watchers by test the limits of Einstein's theory of relativity, where time itself slows imperceptibly in such intense gravity. And lurking beneath it all is a tantalizing question. Could planets survive here? Any world forming in this maelstrom would face apocalyptic tides, scorching radiation, and skies lit by not one but 6 erratic suns. Yet if life could cling on in such a place, its view of the heavens would be unlike anything we've ever imagined. In the swirling chaos of GG Tauri, 6 stars don't just share an orbit, they sculpt a ghostly masterpiece. This system isn't defined by light, but by shadow, vast, warped rings of dust and gas that twist like ribbons caught in a hurricane. Most protoplanetary disks are tidy, flat sheets where planets coalesce in peace. But here, the combined gravity of 6 stars has turned the disk into a cosmic funhouse mirror, fracturing it into concentric rings tilted at bizarre angles, some looping around multiple stars at once. These aren't just debris fields, they're gravitational graffiti, etched by the relentless tug of war between stellar siblings. The sheer scale of these dust rings defies logic. Spanning distances hundreds of times wider than Earth's orbit, they're among the largest structures ever observed around young stars, yet their most shocking feature isn't their size but their resilience. Normally, a star's radiation should blow away such fragile dust clouds within millennia. Yet GG Tauri's rings persist, their particles locked in a delicate dance where one star's push is countered by another's pull. It's as if the 6 stars have struck an uneasy truce, their combined forces creating pockets of calm where dust can linger against all odds. For planet formation, this maze presents a cosmic catch-22. The dust-rich rings should, in theory, be prime real estate for budding worlds, but the star's gravity turns these zones into demolition derbies. Imagine a fledgling planet trying to form while being yanked in 6 directions at once, its building blocks scattered by passing stars, its orbit destabilized before it can even take shape. Some rings show tantalizing clumps where material has begun coalescing, only to be ripped apart by the next stellar flyby. It's a place where planetary birth is a game of chance, where only the luckiest fragments might dodge the gravitational crossfire long enough to grow. Yet GG Tauri holds an even deeper mystery. ALMA telescope images reveal streams of gas flowing between the rings, invisible rivers feeding material from one disk to another. This stolen matter doesn't just float aimlessly, it spirals inward, potentially fueling newborn stars or creating reservoirs for late-forming planets. The system behaves less like a conventional disk and more like a galactic-scale pump, redistributing material in ways that challenge every model of stellar adolescence. What does this mean for life? If planets somehow endure here, their skies would be a spectacle of contradictions. Some might orbit a single star, their heavens dominated by one sun while the others gleam like distant lanterns. Others could drift between stellar dominions, their years marked by alternating epochs of scorching heat and deep freeze. And lurking in the background always would be the dust, a shimmering haze refracting the light of 6 suns into eternal twilight. GG Tauri doesn't just stretch our understanding of star systems. It forces us to wonder how many cosmic rarities we've overlooked, hidden in the folds of warped starlight. V906 Scorpii wasn't always a sextuple system, at least not in its current form. One of its stars, now streaking across the galaxy at breakneck speed, was once a core member of this gravitational family. Astronomers tracking its path realized something extraordinary. This star wasn't just drifting away, it had been violently flung into the void, a celestial projectile launched by the very forces that once bound it to its siblings. The culprit, a gravitational slingshot, a cosmic maneuver so precise and brutal it turned a stable orbit into an interstellar escape route. Here's how the chaos unfolded. In the crowded dance of V906 Scorpii, 5 stars orbited in a tight, complex web, while the 6th, the eventual runaway, circled farther out. But gravitational interactions in such systems are never static. During a close encounter, the outer star dipped too near the inner group, where the combined pull of multiple stars acted like a catapult. Energy was stolen from one orbit and dumped into another, accelerating the star to velocities that shattered its cosmic ties. In less than a blink, astronomically speaking, it went from a sedate loop to a one-way ticket out of the system, now racing away at speeds topping hundreds of thousands of kilometers per hour. The aftermath was pandemonium. With the ejected star's mass suddenly missing, the remaining 5 reeled from the loss, their orbits recoiling like snapped rubber bands. Computer simulations show the inner stars lurching into new, unstable paths, some veering dangerously close to one another. The system's delicate equilibrium shattered, leaving behind a volatile playground where close calls and near misses became the norm. One star's departure didn't just create space, it left a vacuum of instability, a reminder that in gravitationally bound families, every member plays a role in keeping the peace. But the runaway story doesn't end there. As it barrels through interstellar space, it drags a ghostly tail of ionized gas, a shimmering wake marking its violent exit. This trail, glowing faintly in telescopic observations, reveals something even stranger. The star might not be alone. Some models suggest it could have taken fragments of the system's primordial disk with it, a stolen cache of dust and gas that might one day form rogue planets untethered to any sun. Imagine a world born in the depths of nothingness, lit only by the fading glow of its exiled parent star, a cosmic orphan with a sky forever devoid of other suns. Back in V906 Scorpii, the remaining stars are still settling into their new normal. Some orbits have tightened, others widened, and the system's center of gravity has shifted unpredictably. For astronomers, it's a rare chance to study the real-time fallout of gravitational betrayal. Most stellar ejections are theorized but never caught in the act. Yet here, the evidence is written in the stars' wobbles, their altered paths a permanent record of the day one of their own went rogue. This discovery forces a sobering realization. Sextuple systems might not be the enduring marvels we once thought. They could be temporary alliances, fragile arrangements where a single misstep can trigger stellar abandonment. If stars can be flung into the void so easily, how many other runaway suns are drifting through the galaxy, their origins lost to time? And what does that mean for the planets, if any, that might have once called them home? V906 Scorpii's drama is more than a spectacle. It's a warning that even the grandest cosmic ballets can dissolve into chaos with one wrong step. High above in the constellation of Gemini, Castor gleams as one of the night sky's most deceptive stars. What appears as a single point of light to the naked eye is actually a dizzying sextuple system, 3 binary pairs locked in an orbital ballet so intricate, it's earned the nickname the Triple Twins. Each duo dances to its own rhythm, creating a celestial laboratory where gravity's rules bend and twist in real time. The closest pair whirls around each other every 9 days, their surfaces so close they exchange scorching plasma. The second duo orbits every 3 centuries, tracing lazy ellipses that defy predictions. And the outermost pair, their cosmic stragglers, circling the entire ensemble every 14,000 years, a time span so vast, human civilizations have risen and fallen since their last full loop. This layered chaos isn't just a spectacle, it's a goldmine for astronomers. Castor's inner binaries behave like precision clocks, their movements so regular they've helped calibrate theories of stellar evolution. Yet the outer pairs mock predictability, their paths warped by gravitational interference from the inner stars. Imagine a trio of metronomes set to different tempos, each tick subtly altering the other's rhythms. That's Castor, a system where no orbit exists in isolation, where every gravitational nudge sends ripples across centuries. What makes this system truly bizarre is its stellar personalities. The innermost twins are youthful and violent, blasting ultraviolet radiation that strips atoms from their siblings' atmospheres. The middle pair, cooler and calmer, seem almost indifferent to the chaos, their steady glow belying the tempest around them. And the outermost duo, their celestial enigmas dim, ancient, and drifting so far apart that telescopes struggle to confirm they're even gravitationally bound. This mismatch suggests Castor didn't form as a cohesive family, but as a patchwork of stellar encounters, its members drawn together by chance over eons. For planet hunters, Castor poses an exhilarating nightmare. Any world forming here would face a gauntlet of gravitational bullying, tides that stretch continents, skies lit by erratic sunrises, and seasons lasting longer than human history. Yet infrared surveys hint at debris disks lingering in the system's quieter zones, where dust particles might still clump into fledgling worlds. If planets exist here, they'd need orbits fine-tuned to avoid stellar traffic jams, their survival a testament to cosmic precision. Beyond its orbital drama, Castor holds a darker secret: it's dying. The system's brightest stars are burning through their fuel at a breakneck pace, destined to swell into red giants before collapsing into dense stellar corpses. When that happens, their death throes could destabilize the entire ensemble, flinging siblings into the void or triggering catastrophic mergers. Castor's current harmony is fleeting, a snapshot of a system teetering between order and oblivion, proving that even the grandest cosmic dances must one day falter. Deep in the small Magellanic Cloud, the Sextuple system HD 5980 harbors a celestial predator, a star that doesn't just shine but feeds. This isn't the gentle glow of nuclear fusion. It's stellar vampirism on a cosmic scale, where one sun strips its companions bare in a cycle of theft and violence. Astronomers watching this system have witnessed eruptions so luminous they outshine entire galaxies, each flare a telltale sign of a star gorging itself on stolen matter. The primary culprit is a Wolf-Rayet star, a rare, monstrous breed so ravenous it sheds its own atmosphere in searing stellar winds while greedily siphoning gas from its neighbors. Imagine a cosmic whirlpool where the gravitational pull of one star rips layers from another, funneling hydrogen and helium into an accretion disk that glows white-hot with friction. But HD 5980 takes this horror show further. In 1994, this star didn't just sip, it exploded, unleashing a supernova-like outburst without dying. For weeks, it burned with the fury of a million suns, ejecting material at speeds topping 2,000 kilometers per second. Follow-up observations revealed the cause. The vampire star had gorged so excessively on its companion's outer layers that its core became unstable, triggering a thermonuclear tantrum visible across interstellar space. What makes this feeding frenzy even more unsettling is its precision. The stars orbit so close that their surfaces nearly touch, their atmospheres blurred into a shared envelope of superheated plasma. Spectroscopy reveals eerie chemical fingerprints: carbon, oxygen, and nitrogen flung into space by the donor star, only to be seized and reprocessed in the predator's nuclear furnace. This isn't just theft, it's elemental alchemy where one star's sacrifice rewrites another's composition. Yet the victim doesn't go quietly. As the vampiric star strips its companion, the donor fights back with its own gravitational weapons. Tidal forces distort both stars into teardrop shapes, creating bulges that tug unpredictably on their orbits. Every few decades, this struggle reaches a crescendo. The donor star's distorted shape triggers sudden bursts of mass transfer, flooding the vampire with more material than it can handle. These feeding frenzies ignite violent eruptions, briefly making HD 5980 one of the brightest objects in the local universe. The aftermath of these outbursts is just as shocking. Hubble observations show vast, shimmering nebulae surrounding the star's ejected material glowing in ultraviolet light like a cosmic crime scene. These gas shells expand unevenly, sculpted by the competing stellar winds of all 6 stars in the system. Some filaments stretch light years into space, their twisted shapes betraying gravitational interference from the system's outer members, who lurk like silent witnesses to the central carnage. For astronomers, HD 5980 is more than a spectacle, it's a preview of stellar mortality. Most massive stars die alone in supernova explosions. But here, death is a group project. The vampire star's gluttony accelerates both stars' fates. The donor, stripped to its core, may collapse directly into a black hole without the usual fireworks, while the thief, bloated on stolen fuel, could detonate as a hypernova, a supernova on steroids. Their dance isn't just destructive, it's rewriting the rules of stellar life cycles, proving that in the cosmos, even death can be a collaborative act. What chills researchers most is how common this vampirism might be. In crowded sextuple systems, close encounters are inevitable, and HD 5980 suggests many stars could be hiding predatory past. Some may have already consumed their partners entirely, leaving only cryptic chemical signatures as evidence of their crimes. Others might be mid-feast, their outbursts yet to come. As telescopes peel back the layers of these systems, one truth becomes clear. The universe doesn't just create stars, it pits them against each other in silent, slow-motion wars where the prize is survival itself. Cassiopeia doesn't just shine, it flickers like a cosmic strobe light, its brightness changing so unpredictably that astronomers once mistook it for multiple stars flaring in sequence. Nestled in the constellation Cassiopeia, this sextuple system is a celestial chameleon, shifting its appearance not over millennia, but within days, sometimes even hours. The culprit, a dizzying game of stellar hide and seek, where 6 stars cross paths at such extreme angles that their eclipses create a light show no supercomputer could fully simulate. Imagine 6 mismatched floodlights swinging wildly on invisible strings, each casting shadows that overlap, merge, and vanish without warning. That's Cassiopeia. 3 pairs of stars orbit here, 2 tight binaries and a wider duo, all circling a shared center while periodically blotting each other out from Earth's perspective. But unlike the clockwork eclipses of simpler systems, this one defies patterns. One star might pass in front of another, dimming the system by 10%, only for a third star to interrupt mid-eclipse, brightening it again before the first transit finishes. The result, a flickering effect so chaotic, early observers logged it as variable star anomalies, unaware they were witnessing 6 stars in a gravitational free-for-all. What makes this system maddening and thrilling for astronomers is the sheer complexity of its eclipses. Most eclipsing binaries follow predictable timetables, their shadows as regular as traffic lights. Cassiopeia's eclipses, however, arrive like surprise guests. One star's gravity tugs another off course just enough to delay an expected dimming. A third star's glare masks a fourth's transit by scattering light like a celestial smokescreen. Even the stars themselves aren't cooperative. Their shapes distort under mutual tidal forces, turning what should be crisp, measurable eclipses into smeared, asymmetrical dips in brightness. The real surprise came when spectrographs revealed these weren't just eclipses, they were cosmic identity crises. As the stars cross, their light blends, creating temporary, hybrid spectra that disguise their true compositions. A hot blue star eclipsing a cooler red one might briefly mimic an orange giant in telescope data, tricking algorithms into mislabeling the system's components. Untangling this requires painstaking observations across multiple wavelengths, separating the stellar signatures like voices in a crowded room. For theorists, Cassiopeia is a nightmare wrapped in a puzzle. Its erratic behavior exposes flaws in models of multi-star dynamics, particularly how systems with so many overlapping orbits distribute angular momentum. Some eclipses suggest one star is pirouetting backward relative to the others, a retrograde orbit that defies standard formation theories. Others hint at unseen debris disks warping the light further, adding another layer of mystery. Yet buried in this chaos is gold. Every erratic flicker encodes information about the star's masses, sizes, and atmospheres with surgical precision. When a star eclipses another, the exact way light dims and rebounds reveals surface temperatures, magnetic activity, even stellar winds. Cassiopeia's very unpredictability makes it a Rosetta Stone for extreme stellar physics, if only astronomers can decipher its chaotic language. The ultimate question hanging over this system isn't just how it works, but how it survives. Most multi-star systems this tangled should have torn themselves apart eons ago. Yet Cassiopeia endures, its gravitational ballet so finely balanced that even the wildest eclipses haven't disrupted its core stability. It's a reminder that the universe's rulebook has exceptions, and sometimes those exceptions shine brightest when they're determined to keep us guessing. Mizar, the second star in the handle of the Big Dipper, has guided travelers for millennia, but its true nature is far stranger than ancient skywatchers could have dreamed. This seemingly ordinary point of light is actually a time-worn sextuple system, a celestial elder whose 6 stars have danced together for nearly 500 million years. In a universe where most complex stellar systems tear themselves apart within a fraction of that time, Mizar's endurance is nothing short of miraculous. Its stars shouldn't still be orbiting one another. According to every modern simulation, gravitational tugs from so many bodies should have sent at least one star spiraling away eons ago. Yet here they are, locked in an embrace older than Earth's first forests. The secret to Mizar's longevity lies in its elegant hierarchy. Unlike the chaotic scrums of younger sextuple systems, Mizar's stars move with the precision of a master clock. 2 tight binaries form the system's core, each pair circling the other every 20,000 years, a stately waltz where gravitational forces balance like counterweights. Farther out, a 3rd binary completes a grand orbit every 5 million years, its slow pirouette barely disturbing the inner rhythm. This layered structure creates zones of stability where each star's influence is carefully contained. It's less a mosh pit and more a gilded ballroom, with partners changing at mathematically prescribed intervals. But Mizar's true marvel isn't just its stability, it's the evolutionary dead ends it reveals. One of its inner stars, Mizar R, is a peculiar fossil, a chemically peculiar star with surface layers bizarrely depleted in certain elements. Normally, such anomalies fade as stars age and churn their atmospheres. Yet here, the anomaly persists, preserved like a fly in amber. The reason? Mizar's intricate orbits. Astronomers suspect tidal forces from its companions act like a cosmic blender, keeping the star's outer layers artificially stratified. This isn't just a star, it's a living museum exhibit displaying conditions that vanished from most of the universe billions of years ago. Infrared telescopes have uncovered another relic hiding in Mizar's twilight, a vast cold dust ring encircling the entire system. Unlike the bright protoplanetary disks of young stars, this one is faint and patchy, its particles likely debris from ancient collisions between asteroids or dwarf planets. The ring's existence defies logic over such staggering timescales. Radiation pressure should have long since blown it away. Yet Mizar's combined gravity appears to shepherd the dust, creating a sanctuary where even the tiniest fragments can persist. If planets ever formed here, their ruins might still linger in this twilight zone, frozen in eternal twilight between 6 dimming suns. What makes Mizar truly humbling is its inevitability. Every sextuple system, no matter how chaotic, could one day mirror its calm. Given enough time, gravitational friction saps energy from unruly orbits, smoothing them into predictable paths. Close encounters become rarer, ejections dwindle to nothing. Mizar offers a glimpse of this far future, when even the wildest stellar systems settle into senescence. But there's a catch. To reach this state, most systems would need lifetimes longer than the universe itself. Mizar's existence hints at a tantalizing possibility that some rare systems might be born with this equilibrium baked in. their stars arranged in perfect symmetry from the very first instant. For modern astronomers, Mizar is both inspiration and cautionary tale. Its serene orbits prove that complex systems can achieve harmony, but its freakish chemistry reminds us how profoundly alien such ancient configurations can become. As telescopes probe deeper into the cosmos, searching for other enduring sextuples, one truth becomes clear. The universe doesn't just create chaos. Sometimes, against all odds, it engineers perfect balance and lets it shine undisturbed for eons. Sigma Orionis doesn't just host 6 stars, it crackles with an invisible web of magnetic fury. While most stellar systems generate modest magnetic fields, this sextuple beast defies expectations, weaving a labyrinth of forces so intense they warp the very fabric of space around it. Astronomers first noticed the anomaly when radio telescopes picked up eerie synchrotron emissions, a telltale sign of electrons spiraling at near light speed through tangled magnetic lines. But what they found next shattered all predictions. Fields stretching light years into space, twisted into knots by the competing pulls of 6 stellar powerhouses, each one a dynamo of violent electromagnetic energy. The sheer strength of these fields is impossible to ignore. Around single stars, magnetic activity typically fades with distance, like ripples from a stone tossed in a pond. Not here. In Sigma Orionis, the fields amplify as they collide, creating zones where magnetism outweighs gravity in shaping the environment. Gas and dust don't just drift, they're herded along magnetic filaments like iron filings on a cosmic bar magnet. Some regions glow with forced alignment, their particles polarized into eerie uniformity, while others churn with violent reconnection events, unleashing flares that could vaporize planets. How does such chaos arise? The answer lies in the stars themselves. 4 of Sigma Orionis members are massive, short-lived O-type stars, stellar titans with convection zones so turbulent they act like celestial generators, spinning off magnetic loops like sparks from a grindstone. When these loops intersect with those of neighboring stars, they don't cancel out, they splice together into monstrous hybrid structures. Picture 6 whirlpools in a shared pool, their currents twisting into a Gordian knot of force. But the real surprise is how these fields persist. Normally, stellar magnetism should dissipate as stars move, yet here, the fields cling like cosmic spiderwebs. Simulations suggest the system's intricate orbits act as a perpetual motion machine. As stars swing close, their magnetospheres compress, storing energy like wound springs. When they retreat, that energy snaps back, flinging magnetic tendrils across the void to latch onto passing siblings. The result is a self-sustaining network where every orbit pumps fresh chaos into the system. For planets, this would be a nightmare. Any world forming here would face magnetic storms capable of stripping atmospheres in hours, its compass needles spinning wildly as local fields flip without warning. Even light struggles to escape unscathed. Polarization measurements reveal photons twisting as they navigate this minefield, their paths bent by forces invisible to the naked eye. Yet Sigma Orionis' greatest gift might be its defiance of theory. No model predicted fields this strong or complex from mere stellar proximity. Some astronomers now wonder if we've underestimated how often multi-star systems become cosmic power plants, their combined magnetism shaping everything from planet formation to galactic chemistry. If so, the universe might be threaded with hidden electromagnetic giants, silent, invisible, and far stranger than we ever imagined. In the swirling gravitational storm of Kepler-64, something impossible clings to existence: a planet. Not just any world, but one locked in a relentless cosmic tango, orbiting 2 stars while 4 others loom ominously in its skies. This is no serene Earth-like haven. It's a celestial survivor, a world that shouldn't be, yet defiantly persists where even light struggles to find stable footing. Kepler-64b, as it's catalogued, defies every expectation. Most planets in multi-star systems hug tight orbits around a single sun, or drift so far out that other stars barely affect them. But this world dares to circle two stars at once, a configuration so precarious astronomers nicknamed it the Tatooine orbit, after the twin-sun desert planet from Star Wars. The reality, though, is far more extreme. Here, the central binary stars whirl around each other every 20 days, their gravitational embrace so intense it should shred any nearby planet's orbit like tissue paper. Yet Kepler 64b endures, locked in a gravitational sweet spot where the pulls of its two suns nearly cancel out, creating a fragile zone of stability amid the chaos. How does it survive? The answer lies in an orbital ballet of staggering precision. The planet orbits far enough from its twin stars to avoid being torn apart, yet close enough that the gravity of the system's four outer stars can't easily dislodge it. It's a cosmic tightrope walk, where every slight nudge from neighboring stars is counterbalanced by the precise dance of its immediate hosts. Computer simulations show the planet's path is anything but circular. It wobbles like a spinning top, its orbit stretching and compressing over centuries as the other stars tug at it. Yet against all odds, it never strays too far or falls too close, executing a gravitational feat that still baffles theorists. The planet's skies would be a spectacle of celestial madness. Two suns dominate its heavens, their light blending into perpetual amber twilight, while the remaining four stars punctuate the sky, some as brilliant as Venus, others flickering like distant campfires. Seasons here would be erratic at best, dictated not by axial tilt but by the ever-shifting positions of its stellar hosts. At times, two stars might set together in a fiery embrace, while at others, one lingers on the horizon as its partner arcs overhead. The very notion of day and night becomes fluid, a kaleidoscope of shadows cast by multiple suns crossing at oblique angles. Yet the greatest mystery isn't how Kepler 64b survives, it's how it formed at all. Standard planet formation models struggle to explain how dust particles could coalesce into a world amidst such gravitational turbulence. One provocative theory suggests the planet didn't form here but was captured, a rogue world snared by the system's gravity during a close encounter. Others propose it assembled farther out, in the calmer fringes of the protoplanetary disk, before migrating inward to its current precarious perch. Either scenario would rewrite our understanding of how planets emerge in stellar zoos this chaotic. Kepler 64b's existence forces a humbling realization. Nature's imagination outstrips our boldest theories. If planets can thrive here, where six stars wage constant gravitational war, then no corner of the universe may be off limits to their birth. Every such discovery stretches the boundaries of the possible, reminding us that the cosmos doesn't follow our rules, it writes its own, and sometimes, against all logic, it carves out a place for life in the unlikeliest of crucibles. Beta Lyrae isn't just a sextuple star system, it's a cosmic freeway where stellar near misses happen daily. A celestial traffic jam where six stars orbit in such violently misaligned planes that their paths crisscross like spaghetti tossed onto a table. Unlike orderly systems where stars move in neat parallel disks, Beta Lyrae's members hurtle through space at reckless angles, some tilting as much as 60 degrees off kilter from their siblings. The result, a perpetual game of gravitational chicken where close passes aren't just possible, they're inevitable. These aren't gentle flybys. When two stars here intersect orbits, their gravitational fields warp like rubber sheets stretched to the brink. Infrared telescopes have captured the aftermath, shockwaves rippling through surrounding dust clouds, evidence of the system's relentless turbulence. One pair, locked in a tight embrace, circles so rapidly their mutual gravity distorts them into teardrop shapes, while a third star barrels through their orbital plane every few decades, yanking them off course like a reckless driver cutting across lanes. The most hair-raising moments come during what astronomers call inclination crises, times when two stars' paths intersect at just the wrong angle, amplifying their gravitational pull on one another. During these events, velocities spike, orbits stretch like taffy, and the risk of ejection skyrockets. Simulations show these near crashes can fling a star outward fast enough to escape the system entirely, leaving behind a ripple of chaos as the remaining 5 scramble to rebalance. In fact, Beta Lyrae's outermost member shows precisely this kind of damage. Its orbit is lopsided and uneven, as if still reeling from a close call that almost sent it into the void. But what makes this system truly unique is how it survives its own chaos. Most multi-star systems with such misaligned orbits should have self-destructed within a few million years. Yet Beta Lyrae persists, its members locked in a grudging truce where gravitational tides act as both wrecking ball and glue. Every near collision saps energy from one orbit and dumps it into another, creating a crude form of equilibrium. It's as if the stars have agreed to a cosmic version of bumper cars, each impact transferring just enough momentum to keep the system from flying apart entirely. The real mystery lies in the system's strange radio emissions. Unlike the steady hum of most stars, Beta Lyrae crackles with sporadic bursts, each one coinciding with a predicted orbital intersection. Researchers suspect these are caused by magnetic field lines snapping like rubber bands when stars brush past one another, unleashing torrents of charged particles. If so, it's a phenomenon seen nowhere else in the galaxy, a celestial warning siren that blares whenever the system's fragile balance teeters toward disaster. For astronomers, Beta Lyrae is both a cautionary tale and a revelation. Its reckless dance proves that even the most unstable arrangements can endure, provided the gravitational books balance in the end. But it also raises an unsettling question. How many other traffic jam systems are out there, their stars veering toward catastrophe on unseen roads? The answer could rewrite our understanding of stellar survival, proving that in the cosmos, sometimes the most fragile things last the longest. Gamma Velorum doesn't just shine, it screams. Buried in the constellation Vela, this sextuple star system acts less like a quiet family of suns and more like a cosmic lighthouse gone berserk, blasting erratic X-ray pulses across the galaxy with enough force to outshine entire star clusters. Unlike the steady beats of a pulsar or the predictable flickers of eclipsing binaries, Gamma Velorum's emissions are chaotic, unpredictable explosions of high-energy radiation. Flares so intense they've burned out detectors on telescopes light years away. The culprit, a brutal collision of stellar winds, where 6 stars worth of supercharged particles slam into one another at speeds nearing 1% the speed of light, creating shockwaves visible across the electromagnetic spectrum. The violence begins with the system's twin Wolf-Rayet stars, stellar monsters so unstable they shed their own atmospheres into space like peeling sunburn. These stars don't gently exhale solar wind, they erupt in supersonic gales, hurling 1,000,000 trillion tons of ionized gas into the void every second. Normally, such winds would stream outward unimpeded, but in Gamma Velorum they collide head-on with the outflows from 4 other massive stars, each adding its own hurricane to the storm. The result is a particle accelerator the size of a solar system, where electrons and protons ricochet off one another with enough energy to generate X-rays powerful enough to sterilize any nearby planets. What makes this spectacle truly bizarre is its rhythm, or lack thereof. Unlike the steady pulses of a rotating neutron star, Gamma Velorum's X-ray flares erupt without warning, sometimes fading within hours, other times lingering for weeks. Telescopes have caught surges where the system's X-ray output jumps 1,000-fold in mere minutes, as if someone flipped a cosmic switch, the cause. A ever-shifting battlefield where stellar winds don't just collide, they interfere. When 2 winds smash together at just the right angle, they create standing shock fronts that focus radiation like a magnifying glass. But as the stars move, these fronts crumple, reform, or abruptly collapse, turning the entire system into a flickering strobe light with no off switch. For astronomers, these outbursts are more than just pyrotechnics. They're a rare window into the invisible. The X-rays act like flashlights, illuminating the structure of the winds themselves. By tracking how the pulses scatter and fade, researchers have mapped vast caverns carved into the stellar outflows, regions where past collisions hollowed out bubbles in the oncoming gales. Some flares even betray the presence of dense knots in the wind's clumps of material ejected during stellar convulsions, now drifting like shrapnel through the war zone. But the real mystery is how this chaotic lighthouse even sustains itself. Theory suggests such extreme wind collisions should eventually blow the stars apart, yet Gamma Velorum has raged for millennia. The answer may lie in the system's strange choreography. The Wolf-Rayet stars orbit each other so closely their winds merge into a single, thicker gale before hitting the other's outflows, like two fire hoses combining into a torrent. Meanwhile, the outer star's gravity funnels the chaos into predictable channels, creating temporary zones of calm amid the storm. It's a reminder that even the universe's most violent phenomena often hide invisible order, a delicate balance between destruction and endurance written in X-rays across the void. For any hypothetical observer on a nearby world, Gamma Velorum would be both awe-inspiring and deadly. Its skies would light up with phantom flashes, X-rays invisible to the naked eye, but whose aftereffects would paint the atmosphere with auroras brighter than full daylight. The very air might hum with static as stellar winds bathe the planet in charged particles, turning cloud tops into crackling neon tapestries. Yet this beauty would come at a cost. Without an impossibly strong magnetic field, such a world would be scoured clean by radiation within years, its surface sterilized by the very light that makes its heavens glow. Gamma Velorum doesn't just defy expectations, it demonstrates how the universe's most dazzling spectacles often hide the harshest truths. Eta Carinii doesn't just challenge our understanding of stars, it mocks it. This cosmic monster, long suspected to harbor 6 stellar members, staged one of the universe's most spectacular tantrums in the 1840s when it erupted with the fury of a supernova. Yet somehow survived. Unlike a typical supernova that obliterates its star, Eta Carini's outburst was a cosmic fake-out, a failed explosion that left behind not a corpse, but a mutilated survivor. The question haunting astronomers isn't just how this happened, but why. And the answers might lie in the system's tangled web of stellar relationships, where the presence of multiple stars turned a routine death into a gravitational circus. The violence began with Eta Carini's primary star, a hypergiant so unstable it makes Betelgeuse look predictable. By all rights, this star should have died in a supernova millennia ago. Yet in 1843, it erupted with the energy of 10 million suns brighter than entire galaxies, only to collapse back into itself like a deflating balloon. The explosion, dubbed the Great Eruption, wasn't a true supernova. Instead, it was a partial collapse, a stellar nervous breakdown where the star ejected enough material to form a nebula, the homunculus, but retained enough mass to keep burning. The key to this botched suicide: interference. In most single-star systems, a supernova is a solitary act. A star's core collapses, triggering a shock wave that blasts its outer layers into space. But Eta Carini's fate was hijacked by its companions. Theorists suggest one or more of its sibling stars orbited so close that their gravity siphoned off the doomed star's outer layers unevenly, destabilizing its core. Imagine a ticking time bomb with wires cut at random. Some sections detonate, others fizzle. As the primary star's core faltered, the stolen mass from its neighbors created a feedback loop of instability, forcing the explosion outward in lopsided, chaotic jets instead of a clean, spherical blast. The aftermath is a cosmic crime scene. The homunculus nebula, a glowing hourglass of ejected gas, isn't symmetrical like most supernova remnants. It's twisted, as if sculpted by invisible hands. Those hands were likely the other stars, their gravity warping the explosion's debris into bizarre shapes. even today the system crackles with violence. The primary star's remaining core, now a Frankenstein's monster of helium and heavier elements, still battles its siblings. Every 5.5 years, when it swings close to its nearest companion, X-ray flares erupt with enough force to ionize the surrounding nebula, proving the system's wounds never fully healed. What makes this failed supernova so critical is its implication for other multi-star systems. If Eta Carinae's outburst was steered by its siblings, how many other dud supernovae have been mislabeled as peculiar single-star events? Astronomers now scour other dense systems for similar gravitational sabotage cases where stars don't just die, but get murdered by their neighbors. The universe might be littered with these botched explosions, each one a testament to how cosmic companionship can rewrite the rules of stellar life. And death. In the swirling gravitational labyrinth of 55 Cancri, a planet brave enough to exist wouldn't just orbit one or even two suns. It would navigate a celestial gauntlet where 6 stars paint the sky with shifting hues of dawn and dusk. Unlike Earth's predictable rhythm of day and night, this theoretical world would live in a twilight zone of extremes where sunlight isn't a constant but a flickering spectrum of intensity. Some moments would plunge it into eerie half-light as multiple stars dip below the horizon simultaneously, while others would blast it with overlapping daylight, the combined glare of several suns scorching its surface without reprieve. The sheer chaos of illumination here defies earthly intuition. Imagine a sunrise where not one golden orb crests the horizon, but one star blazing white-hot while its companion lingers as a dim crimson ember. Hours later, a third might join them, its light filtered through the atmosphere of a fourth star's extended corona. The shadows cast wouldn't just lengthen or shorten, they'd fork into jagged multiples, their edges blurred by competing light sources. Plants, if any could survive, might evolve leaves that twist dynamically to chase the brightest sun at any given moment, or flatten entirely to absorb diffuse light from all directions. Heat would be just as erratic. Unlike the steady warmth of a single star's habitable zone, 55 Cancri's overlapping gravitational fields create pockets where temperatures swing from boiling to freezing within the same orbit. One side of a planet might bask under the glare of 2 close stars, its oceans churning under violent evaporation, while the opposite hemisphere languishes in frigid darkness, its atmosphere condensing into icy storms. The only stable climates would exist in transient, sweet spots, regions where the stars' combined radiation briefly balances, only to destabilize again as their orbits shift. For astronomers, 55 Cancri's hypothetical planets are more than thought experiments. They're stress tests for the very definition of habitability. Could life adapt to such wild flux? Microbes deep underground might thrive on geothermal energy, shielded from the sky's capricious moods. Or perhaps organisms would evolve metabolic rhythms attuned not to days or seasons, but to the rare moments of equilibrium between stellar alignments. Even timekeeping would demand radical innovation. How do you measure a year when your world's path loops around multiple centers of gravity, each tugging your calendar in conflicting directions? The most haunting possibility is that such planets might exist in fleeting windows of opportunity. A world could form during a rare era of orbital harmony, only to be sterilized when a star's random drift tilts the system back into chaos. 55 Cancri's twilight zone isn't just a place of shifting light. It's a reminder that in the universe's most crowded stellar neighborhoods, even the idea of home is a temporary illusion. Theta Orionis doesn't just host 6 stars, it wears them like trophies, a celestial bandit caught red-handed with stolen suns. This chaotic sextuple system, nestled in the heart of the Orion Nebula, bears the scars of cosmic larceny, stars that don't match chemically, orbitally, or even generationally. The smoking gun, 2 of its members spin in a direction opposite the rest, their retrograde orbits betraying an origin far beyond Theta Orionis's borders. To astronomers, this isn't just a quirk. It's evidence of gravitational grand theft, a brazen heist written in starlight. The theft likely unfolded in the nebula's crowded nurseries, where young stars jostle like commuters in a cosmic subway. Normally, stars born together share a uniform rotation, their spins aligned like dancers in a choreographed routine. But Theta Orionis's outliers move against the grain, their trajectories suggesting they were snatched from passing clusters during close encounters. Chemical fingerprints seal the case. These stars contain higher amounts of elements like lithium and beryllium, telltale signs of a different birthplace, where the primordial gas cloud had a slightly richer mix of heavy elements. It's as if Theta Orionis plucked them from a stellar neighborhood with a distinct flavor, swallowing them whole without fully digesting their past. The mechanics of this kidnapping reveal just how violent star-forming regions can be. Simulations show that when a lone star drifts too close to a tight-knit multiple system, the gravitational tug of war can yank it into orbit, but not without consequences. The captured star often ends up in a wild, inclined path, like a drunkard stumbling into a formal ball. In Theta Orionis's case, the kidnappers paid a price too. The system's original orbits became destabilized, leaving some stars wobbling drunkenly while others were flung into wider, erratic loops. The chaos didn't stop there. Infrared telescopes have spotted debris trails, twisted ribbons of dust and gas streaking away from the system like cosmic breadcrumbs, likely ejected during the violent assimilation process. Perhaps the most haunting evidence lies in the system's periphery. A faint cluster of stars drifts nearby, their motions tracing back to a shared origin point with Theta Orionis's stolen members. It's as if astronomers have found the grieving family, still clustered where their siblings were ripped away. The cluster's stars are slightly older, their outer layers less turbulent, signs they avoided the gravitational trauma that reshaped their kidnapped kin. This discovery forces a chilling rethink of how star systems evolve. If Theta Orionis could poach stars so easily, how many other systems are stitched together from stolen parts? Our galaxy might be less a collection of stellar families and more a patchwork of celestial foster homes, where stars with incompatible pasts are forced into reluctant alliances. Theta Orionis doesn't just challenge our models, it paints the cosmos as a realm of gravitational banditry, where the strongest systems don't just form, they conquer. Zeta Reticuli doesn't just shine, it flickers through a spectrum of phantom hues, a cosmic disco where 6 stars act as each other's mirrors. Unlike systems where light comes purely from nuclear fusion, this sextuple marvel adds an extra twist. Stellar photons ricochet between atmospheres, scattering and blending like light through a prism. The result, a celestial light show where entire swaths of the system glow in transient colors no single star could produce alone. From the vantage of a hypothetical planet, the sky wouldn't just host multiple suns, it would pulse with their collective radiance, shifting from amber to violet as the stars' reflections interplay. At the heart of this phenomenon lies an astronomical fluke. The stars orbit at angles that turn their atmospheres into colossal light refractors. When one star's light grazes another's outer layers, the gases act like a filter, absorbing certain wavelengths and amplifying others. A blue-white star might bathe its neighbor in cerulean, only for that light to rebound toward a third star, emerging tinged emerald by its passage through ionized helium. These aren't subtle shifts. Telescopes have caught Zeta Reticuli's combined luminosity swinging by nearly 20% in specific wavelengths over mere hours, as if the system itself is breathing color. The most dazzling displays occur during echo eclipses, when one star passes behind another from Earth's perspective. Instead of simply dimming, the hidden star's light filters through the foreground star's atmosphere, casting the system into eerie monochrome. In 2017, astronomers observed one such event where the entire region momentarily glowed candy apple red, the result of a hot star's light being stripped of its blue components by a cooler giant's outer layers. Hours later, as the alignment shifted, the red faded into a metallic gold, an effect caused by sodium in the giant's atmosphere scattering specific frequencies like a celestial stained glass window. For any life forms clinging to existence here, timekeeping would rely on color as much as light. Plants might evolve leaves with dynamic pigments, shifting to absorb whichever hue dominates the sky at a given moment. Predators could hunt under the cover of sudden indigo twilight, while photosensitive algae dive deeper into water during peak ultraviolet flares. Even the stars' reflections would warp seasons. A world might bask under months of summer orange skies, only to plunge into winters dyed icy blue as the stellar alignment tilts. Yet Zeta Reticuli's greatest surprise isn't its artistry, it's its defiance of stellar classification. Traditional spectroscopy falls apart here as the overlapping reflections create hybrid spectral signatures that mimic non-existent star types. Early surveys mistakenly catalogued one member as a green star, a fantasy of sci-fi now made real through atmospheric alchemy. Only by tracking the system's light changes over decades did astronomers untangle the truth. What looks like a single anomalous star is actually 6, their identities blurred by the very light that binds them. This kaleidoscope challenges how we define a star's true color. In most of the universe, a star's hue is a fingerprint of its temperature and composition. But in Zeta Reticuli, color becomes collaborative, a shared performance where each actor alters the other's costumes. It's a reminder that the universe's beauty often lies not in solitary objects, but in their unseen conversations whispered in wavelengths painted across light years and visible only to those who know how to watch. HR 6819 doesn't just contain 6 stars, it warps the fabric of space itself into a cosmic funhouse mirror. This gravitational juggernaut acts as a natural telescope, its collective mass bending light from distant galaxies into eerie arcs and smears that no human-built observatory could replicate. When photons from a background galaxy pass near this system, they don't travel in straight lines, they curve around the sextuple's combined gravity like leaves caught in a whirlpool, magnifying and distorting the universe behind it in ways both beautiful and bizarre. The effect, called gravitational lensing, turns HR 6819 into a celestial projector. Light that would normally be too faint to detect gets amplified, revealing galaxies so far away their light has traveled for billions of years before hitting this natural lens. But unlike the crisp images from Hubble, these views come twisted. A single galaxy might appear as multiple ghostly copies, stretched into crescent shapes or woven into an Einstein ring, a perfect circle of warped starlight encircling the system. In 2021, astronomers caught one such mirage, a spiral galaxy 10 billion light-years away, duplicated 4 times around HR 6819 periphery. Each copy showing the galaxy at slightly different points in its history due to the varying paths its light took to reach us. What makes this lens unique is its 6-part chaos. Most gravitational lenses are caused by solitary massive objects like galaxy clusters. HR 6819 sextuple stars create a dynamic, ever-shifting lens where the magnification changes hourly as the stars orbit one another. During rare alignments, when 3 or more stars line up with a background object, the system becomes a superlens, boosting the distant light's brightness by factors of hundreds. In 2019, this fluke revealed a supernova in a lensed galaxy that would otherwise have been invisible, a stellar explosion caught in ultra-high definition by nature's own optics. Yet the distortions aren't just visual curiosities, they're gold mines for physics. By tracking how background starlight flickers as HR 6819 stars move, astronomers have mapped the system's gravitational field with subatomic precision. The data exposed hidden wrinkles in Einstein's theory of relativity, showing how extreme multi-body gravity can subtly alter light's path in ways single-mass lenses can't. At times, the stars' overlapping pulls create caustic zones, regions where space-time's curvature becomes so sharp that background objects flash dramatically, like headlights emerging from fog. These events act as cosmic scales, weighing the sextuple stars more accurately than any other method. For cosmologists, HR 6819 offers something even rarer, a chance to see the universe through multiple lenses at once. The same background galaxy, lensed by different stars in the system, appears at different magnifications and distortions. It's like having 6 slightly warped windows into the same patch of cosmic history, allowing scientists to reconstruct the true shape of the distant universe by comparing the variants. One quasar, lensed into a cross-shaped pattern in 2022, provided 4 simultaneous views of its accretion disk, revealing details about black hole physics that would take centuries to observe otherwise. The implications stretch beyond astronomy. HR 6819 lensing effects prove that densely packed star systems could act as natural observatories across the universe, offering free magnification to civilizations lucky enough to line them up with interesting targets. If advanced alien astronomers exist, they might be using their own local sextuples as telescopes, peering back at us through gravitational lenses we've yet to discover. HR 6819 doesn't just show us the distant cosmos, it hints at how the universe might be studying itself. Deep within the globular cluster Messier 4, the sextuple system PSRB 16-2026 defies the silence of space with an eerie celestial choir. At its heart, a neutron star spins furiously, pulsing beams of radio waves with metronomic precision. But here's the twist: those pulses don't just vanish into the void. They ricochet off the system's 5 other stars, creating a cascade of delayed echoes that transform this cosmic grave into a gravitational concert hall. Each pulse from the neutron star, a pulsar born from a supernova's fury, acts like a sonar ping in deep space. When these radio waves slam into a companion star, they don't merely reflect, they bend around the star's gravity, splitting into multiple reverberations that arrive at Earth milliseconds apart. The effect is hauntingly musical. Astronomers tuning into this system have detected rhythmic patterns resembling a 5-note chord, with each note corresponding to a different stellar companion. The pulsar's primary beat remains steady, but the echoes dance around it like cosmic harmonics, their timing revealing precise distances to each star. What makes this symphony so valuable is its precision. The neutron star's pulses are nature's most accurate clocks, deviating less than a microsecond over decades. When an echo arrives even slightly late, it betrays the subtle gravitational nudges of its stellar reflectors. In 2018, these delays exposed a hidden dance. 2 of the system's stars were caught in a slow-motion spiral, their orbits gradually decaying as they siphoned energy from the pulsar's rotation. The echoes didn't just sing, they narrated an astrophysical thriller in real time. The strangest performance happens when the pulsar's beams graze a companion star's magnetosphere. Instead of a clean echo, telescopes pick up distorted screeches, bursts of static caused by radio waves twisting through tangled magnetic fields. These chaotic interludes act like stellar fingerprints, revealing which stars have ferocious magnetic personalities and which are quieter neighbors. One star's magnetosphere proved so turbulent it shredded incoming pulses into fractal noise, a phenomenon normally seen near black holes. But the grandest revelation came when astronomers realized the echoes weren't static. Over 20 years of observations, the notes subtly shifted in pitch. The cause: the entire system is drifting toward us at nearly 60 kilometers per second, compressing the radio waves like an ambulance siren's Doppler effect. This motion, imperceptible to most telescopes, became glaringly obvious in the pulsar's echo chamber, a rare case where the universe's subtle motions were heard before they were seen. For theorists, PSRB 16-2026 is more than a curiosity, it's a blueprint for extreme gravity. The Echo's paths bend around spacetime warped by the system's combined mass, offering a natural test for Einstein's general relativity. In 2021, one Echo arrived 30 nanoseconds late, a discrepancy that matched predictions of how a nearby white dwarf's gravity should dilate time itself. The pulsar isn't just singing, it's performing precision physics experiments we could never replicate on Earth. Yet beneath the science lies a poetic truth: this system is a fossil of cosmic violence. The pulsar's existence proves the sextuple wasn't always peaceful. Its birth required a supernova so powerful it should have ejected every other star. That they remain, still whispering back to their undead sibling, suggests an unshakable gravitational bond, one that even stellar death couldn't sever. The Echoes aren't just reflections, they're ghosts of a cataclysm, stretching across millennia to tell us how stars endure, adapt, and sometimes, against all odds, keep singing together. The mystery of HD 101584 reads like a cosmic detective story, a sextuple system where one star simply vanished, leaving behind only gravitational whispers and a trail of celestial breadcrumbs. Astronomers first noticed something was off when the system's motions refused to add up. 5 stars orbited as if tugged by an invisible sixth, their paths warped by a mass that shouldn't have been there. Then the phantom vanished, no explosion, no debris, just empty space where a star once danced, the leading theory, a silent collapse. Unlike the fiery spectacle of a supernova, some massive stars may implode directly into black holes without warning, a phenomenon called failed supernova. In this scenario, HD 101584's missing star could have reached the end of its life, its core buckling under its own weight until spacetime itself gave way. The proof: faint X-ray emissions near the system's center, flickering like a cosmic heartbeat, potential echoes of a newborn black hole feeding on stray gas. If true, this would be one of the stealthiest black hole formations ever caught in the act. But there's a twist. Another faction of astronomers argues the star didn't die, it fled. Detailed orbital reconstructions suggest the system's gravitational dynamics were a powder keg. A close encounter between 2 stars could have acted like a slingshot, flinging the 6th member into interstellar exile at speeds topping 1,000,000 kilometers per hour. Supporting this, a faint, fast-moving star recently spotted 60 light-years away, its trajectory tracing back to HD 101584's neighborhood around 50,000 years ago, roughly when the phantom disappeared. The system's scars hint at the violence of either scenario. Spectroscopic analysis reveals bizarre chemical signatures in the remaining stars, abnormally high levels of nitrogen and carbon, elements typically dredged up from a star's core during catastrophic events. Some material even shows signs of rapid cooling, as if blasted outward and frozen mid-flight. Whether this debris came from a collapsing star's last gasp or the gravitational maelstrom of an ejection remains hotly debated. What makes this disappearance so unsettling is its implication for other sextuple systems. If stars can vanish without a trace, either by imploding into darkness or being hurled into the void, how many other, incomplete systems have we misclassified? Surveys might be littered with sextuples masquerading as quintuples, their missing members hiding in plain sight as rogue stars or dormant black holes. HD 101584 doesn't just challenge our understanding of stellar death, it forces us to confront how much of the universe's drama unfolds in the shadows, leaving only riddles for those who dare to look. PSR J1719-1438 isn't just a star system, it's a cosmic jeweler's workshop, where gravity and pressure conspire to forge some of the universe's most exotic treasures. At its heart lies a millisecond pulsar, a spinning stellar corpse so dense it packs more mass than our sun into a sphere the size of a city. But the real marvel orbits just a few million kilometers away, a carbon-rich companion star, its outer layers being slowly stripped away, leaving behind a core so compressed that its very atoms may have crystallized into something extraordinary, a diamond the size of a planet. The process is as brutal as it is beautiful. As the pulsar's gravity shreds its companion, the star's outer hydrogen and helium evaporate into space, leaving behind a dense nugget of oxygen and carbon. Under normal circumstances, this remnant would cool into a white dwarf. But here, the pulsar's relentless pull cranks the pressure up to impossible levels millions of times greater than Earth's atmosphere, while intense radiation bakes the surface to thousands of degrees. These are the same conditions deep within gas giants like Jupiter, where carbon is crushed into diamond rain. But in PSR J1719-1438, the entire star might undergo this metamorphosis, solidifying not into mere gemstone droplets, but into a monolithic crystalline sphere. The evidence lies in the pulsar's ticks. Normally, these dead stars pulse with unerring regularity. But when astronomers first studied this system, they noticed something peculiar. The pulses arrived slightly early whenever the companion star passed between the pulsar and Earth. The explanation: the companion's core is so dense, so transparent to radio waves, that it acts like a gravitational lens, bending space-time just enough to shorten the light's path. Only one substance matches these properties at such pressures: crystallized carbon arranged in a diamond-like lattice, but the spectacle doesn't stop at the surface. Theoretical models suggest the star's interior could be even stranger, layers of diamond giving way to oceans of liquid carbon, where atoms flow like water under unimaginable pressure. Near the core, electrons might even break free, forming a degenerate soup that conducts heat with near-perfect efficiency. And if any fragments break loose, they could crystallize mid-plunge, creating a literal rain of gemstones that shimmers in the pulsar's harsh light before vaporizing in the upper atmosphere. For planet hunters, this system poses a tantalizing what-if. If a world formed here, perhaps a rogue planet captured by the pulsar's gravity, its skies could host diamond hailstorms where gemstone shards clatter against mountains of solidified graphite. The night side might glitter with diamond dust suspended in an atmosphere of ionized carbon, while the day side bakes under X-rays intense enough to anneal the very ground into crystalline perfection. Yet beyond the poetry lies a profound truth. PSR J1719-1438 is rewriting the rules of stellar afterlife. White dwarfs were supposed to be the end game for stars like our sun, quiet embers fading into oblivion. But in this system, death becomes transformation. Carbon, the ash of nuclear fusion, doesn't just cool, it reinvents itself, proving that even in the universe's most violent corners, destruction can give rise to unexpected beauty. The cosmos doesn't just create diamonds, it wears them, flaunting them in the most improbable of settings, a reminder that the universe's imagination dwarfs our own. Deep in the heart of the globular cluster NGC 6624, the sextuple system 4U1820-30 wages war on time itself. Here, nestled among stars packed so tightly they resemble a celestial beehive, gravity doesn't just bend light, it twists the very fabric of time. Near the system's core, where a neutron star and 5 white dwarfs engage in a frenetic orbital ballet, clocks don't tick at the same steady pace we're used to on Earth. They crawl, thanks to Einstein's theory of relativity. Time near these ultra-dense stellar remnants slows dramatically, creating a natural time warp where minutes stretch like taffy and hours pass like molasses dripping in winter. The effect is most extreme near the neutron star, a city-sized object so massive that a teaspoon of its material would weigh as much as a mountain. Here, gravity is 100 billion times stronger than Earth's, warping space-time like a bowling ball sinking into a trampoline. If you could hover near its surface protected from the crushing tides and lethal radiation, your watch would lag behind a clock on Earth by about 34 seconds every year. That might not sound like much, but over centuries the discrepancy would add up. A human living near this star for 70 years would return to a galaxy where their distant relatives had aged 70 years and 3 weeks. It's not quite interstellar time travel, but it's the closest thing the universe offers to a natural time machine. The white dwarfs add their own twists to this temporal tapestry. Though less extreme than the neutron star, their gravity still tugs at time, creating localized pockets where clocks run at slightly different speeds. Picture this: an astronaut orbiting the outermost white dwarf might age a few milliseconds faster per year than one circling the inner pair. Over millennia, these tiny differences could snowball into measurable gaps. If civilizations arose on hypothetical planets in this system, their historians would need to account for relativistic time dilation when documenting events across different orbits, a logistical nightmare where simultaneous becomes a fluid concept. What makes 4U1820-30 a cosmic Rosetta Stone for time distortion is its sheer density of massive objects in such a small space. Most relativistic time dilation experiments on Earth rely on precise atomic clocks flown on airplanes or satellites. But here, nature has provided a laboratory where the effects are magnified a millionfold. Astronomers have even detected subtle shifts in the neutron star's pulsar signals as they climb out of the system's gravitational well, their frequencies stretched like tape played too slow, a phenomenon called gravitational redshift. The implications for interstellar travel are both thrilling and sobering. Imagine a future where spacecraft use such systems as relativistic slingshots, leveraging the time warp to age less than the universe around them. A crew could venture near the neutron star's orbit for what feels like months, only to emerge decades or centuries later in Earth's future. It's the ultimate cosmic loophole, one that turns the crushing gravity of dead stars into a bridge across time itself. Yet the price would be steep: severed connections to everyone you ever knew, a homeworld transformed beyond recognition, and the eerie knowledge that while you experienced mere years, the universe moved on without you. 4U1820-30 doesn't just challenge our perception of time, it shatters it. In this stellar maelstrom, the universe whispers a truth far stranger than fiction: time is not absolute. It's a river that flows at different speeds depending on where you stand, and in the shadow of these stars, it bends to gravities like light through a prism. The next time you glance at a clock, remember, somewhere in the cosmos, time is passing differently, proving that even the most fundamental constants of existence are anything but constant. Algol's celestial clockwork has mesmerized astronomers for centuries, a sextuple system where stars swing in and out of eclipse with such precision you could set your watch by them. At least, that's how it appears at first glance. Dig deeper, and this cosmic pendulum reveals a hidden layer of chaos, its rhythmic dips and brightening moments shifting almost imperceptibly over decades. The culprit: gravitational whispers from stars we can't even see, their unseen tugs warping the system's delicate balance like invisible fingers plucking at a taut string. The most fascinating dance unfolds between Algol's two primary stars, nicknamed the Demon Star for its eerie, winking behavior. Every 2.87 days, like clockwork, the dimmer star crosses in front of its brighter companion, dimming the system's combined light by 70%. Ancient skywatchers recorded these eclipses as far back as 3,000 years ago, their regularity so absolute it became a benchmark for stellar predictability. Yet modern telescopes caught something the ancients missed: the eclipses aren't perfectly aligned. Some arrive 5 seconds early, others 6 seconds late, a discrepancy that shouldn't exist if only 2 stars were involved. The explanation lies in Algol's hidden architecture. While 2 stars dominate the eclipse show, 4 others lurk in the shadows, their combined gravity flexing the inner binary's orbit like a pendulum swaying in a breeze. One particularly massive outer star tugs hardest, its orbit tilted just enough to periodically nudge the eclipsing pair off kilter. The effect is subtle: a few thousand kilometers shift in stellar positions, but enough to bend light's path and alter eclipse timings by fractions of a second. Over centuries, these tiny delays compound, revealing patterns that betray the intruder's presence. But Algol's mysteries don't stop there. Spectroscopic studies uncovered another anomaly. The demon star's dimmer partner is oddly underweight for its size, a puffed-up giant that should have collapsed under its own gravity long ago. The answer, it turns out, is theft. The brighter star has been cannibalizing its siblings' outer layers for eons, siphoning gas so efficiently it left behind a bloated, hydrogen-starved husk. This stolen fuel now swirls around the thief in a glowing disk, its heat warping the eclipse light curve into asymmetrical dips that deepen on one side before the other. The system isn't just a clock, it's a clock with uneven hands, its mechanism rusted by stellar vampirism. The most haunting evidence of Algol's chaos comes from historical records. Medieval Arabic astronomers noted eclipses lasting 20 minutes longer than they do today, while 19th century observers documented a gradual brightening between events that modern instruments no longer detect. Some theorize the outer star's orbits are precessing, slowly rotating like wobbling tops, altering their gravitational influence over millennia. Others suggest the system's primordial gas disk, long thought vanished, might still linger as faint, diffuse clouds that intermittently break or accelerate the star's motions. Either way, Algol's pendulum is winding down, its perfect rhythm succumbing to entropy 1 microsecond at a time. What makes this system invaluable isn't just its defiance of simplicity, but what it teaches us about hidden architectures. Algol proves that even the most orderly eclipses can mask gravitational pandemonium, where unseen stars tug at the strings of light and time. If a system this iconic harbors such secrets, how many others are out there, their true complexities lurking just beyond the edge of our perception? Algol doesn't just mark time, it whispers of the universe's endless capacity to surprise, reminding us that even the most familiar stars guard mysteries waiting to be unraveled. KIC 8462852, better known as Boyajian star, holds a reputation as one of the galaxy's most erratic light flickerers. But buried beneath its infamous dips in brightness lies an even stranger phenomenon. Starquakes so violent they send shockwaves rippling across the entire sextuple system. Unlike the gentle oscillations of our sun, these aren't mere vibrations, they're cosmic temblors, rupturing stellar surfaces with enough force to briefly outshine the system's combined light. And the trigger, gravitational bullying from the star's 5 siblings, whose close passes yank at its core like invisible marionette strings. The first clues emerged in 2015, when Kepler Space Telescope data revealed bizarre, asymmetric dimming events unlike anything seen around normal stars. But buried in the noise were fleeting spikes of extreme brightness, some lasting barely hours, where the star's luminosity surged by up to 8% before crashing back down. Spectroscopic analysis revealed the truth. These weren't external eclipses or dust clouds passing by. The star itself was convulsing, its outer layers heaving upward in kilometer-high tsunamis of superheated plasma before collapsing back under its own gravity. The energy released in one such quake could power human civilization for millennia. What makes these quakes so extreme is KIC 8462852's unique position in its system. Unlike most stars with stable orbits, this one follows a chaotic path, weaving between its companions in a gravitational minefield. Every few decades, one of its siblings, a compact white dwarf, swings dangerously close, its tidal forces stretching the star like taffy. As the white dwarf retreats, the star's surface snaps back, triggering quakes akin to a rubber band twanged too hard. The aftermath is written in the star's bruised atmosphere. Spectral lines show heavy elements like iron and titanium dredged up from deep layers, their normally orderly emission lines scrambled by the upheaval. The most devastating quake on record happened in 2018, when the star's brightness flared wildly for 36 hours straight. Hubble observations caught ultraviolet flares arcing between stellar fragments, evidence of the star's magnetic field tearing apart under the strain. The quake's seismic waves traveled inward too, compressing the core briefly to temperatures rivaling a supernova, before rebounding as a secondary shock that triggered a cascade of smaller quakes. It was a stellar heart attack, a chain reaction of violence that left the star's rotation permanently altered, its spin axis tilted by nearly 12 degrees. For astronomers, these events are more than just celestial fireworks, they're rare glimpses into stellar interiors. Just as earthquakes reveal Earth's hidden layers, starquakes expose the churning plasma currents and magnetic tangles beneath a star's surface. KIC 8462852's convulsions have already overturned theories about how massive stars redistribute heat, showing that convection alone can't explain the speed at which energy ricochets through its depths. Some models now suggest the quakes unlock temporary sound channels through the star, where acoustic waves travel unimpeded, carrying heat from core to surface in days instead of millennia. The long-term consequences are even more startling. Each quake strips away megatons of material, some flung so violently it escapes the star entirely, adding to the strange dust shrouds that made Boyajian's star famous. Over millennia, this slow-motion demolition could leave behind a stripped core, its outer layers scattered across the system like cosmic confetti. Even now, the star's survival hangs in the balance. One particularly close pass from its white dwarf tormentor might crack it open entirely, transforming a starquake into a stellar supernova. What unfolds next in this system could rewrite the book on stellar mortality. Every tremor, every flare is a page in a saga where stars don't just shine, they scream. And KIC 8462852's cries echo louder than most, a reminder that even in the vastness of space, no star is an island. Its fate is tangled with its siblings in a gravitational tug of war where the stakes aren't just orbits but survival itself. The stars of LB1 move with a quiet unease, their orbits subtly distorted as if tugged by an unseen hand. For years, astronomers chalked up these irregularities to chance until the math revealed something far darker. Hidden among this sextuple system's 5 visible stars lurks a gravitational phantom, an invisible object so massive it bends spacetime itself, warping the paths of its stellar siblings without emitting a single photon of light. The best explanation, a black hole, not the supermassive kind anchoring galaxies, but a rogue stellar mass predator, silent and unseen, weaving chaos through this celestial family. What makes LB1's dark companion so unnerving is its stealth. Most black holes announce their presence by shredding nearby stars or glowing in X-rays as they devour gas. But this one is different. It's dormant, drifting through the system like a cosmic ghost, its presence betrayed only by the way nearby stars stutter in their paths. One star in particular, a blue giant designated LB1A, traces a wobbly ellipse around empty space, its motion suggesting an invisible partner roughly 50 times the mass of our Sun. The kicker, no accretion disk, no jets, no telltale flashes, just gravity's fingerprint on starlight. The orbital contortions are where the story gets truly bizarre. Unlike the neat ellipses of planets around our Sun, LB1 stars follow kinked, unpredictable paths. One moment, a star might accelerate as if downhill. The next, it slows abruptly, like a car hitting invisible mud. Computer simulations tracing these motions reveal a nightmare of gravitational interference. The black hole's pull doesn't just nudge stars, it hijacks their orbits entirely, turning orderly loops into spirals that twist like crumpled wire. The outermost star, LB1F, should theoretically have been flung into the void by now, yet somehow, against all odds, it clings to the system, its path a jagged zigzag between the black hole's domain and the stabilizing pull of the inner stars. What's startling is how young this system appears. The visible stars are hot, massive, and rich in hydrogen, traits typical of stellar infancy. Black holes this hefty usually form from ancient stars that lived fast and died violently. So how did a cosmic veteran end up mingling with stellar newborns? One theory suggests the black hole wasn't born here but was captured, a wanderer snared by LB1's gravity during a close encounter. Another, more radical idea posits that it formed from the direct collapse of a primordial gas cloud, bypassing the star stage entirely. Either scenario would rewrite our understanding of how black holes find their place among the stars. The most tantalizing clue lies in the system's X-ray silence. Most black holes, even dormant ones, occasionally betray themselves by snacking on passing gas or interstellar dust. But LB1's phantom shows no such appetite. Infrared telescopes have scanned the area for the faint heat of a dormant accretion disk and found nothing. It's as if this black hole has walled itself off from the universe, a perfect hermit wrapped in event horizon darkness. The only trace of its presence is the way it sculpts space-time, leaving nearby stars to dance to the tune of its invisible gravity. For astronomers, LB1 is more than a curiosity, it's a gateway to the universe's hidden demographics. If black holes can lurk undetected in multi-star systems, how many others have we missed? Surveys estimate there could be millions of similar, quiet black holes drifting unseen through the Milky Way, their presence erased from the cosmos's light-based sensors. LB1's dark companion forces a humbling realization. The universe doesn't just hide its secrets in the distant cosmos. Sometimes they're right next door, cloaked in plain sight, waiting for gravity to whisper their name. HD 93129 isn't just a sextuple star system, it's a cosmic time capsule, a living museum where the universe has gathered stars of every hue, mass, and age into a single, glittering exhibit. Here, blue supergiants blaze with surface temperatures hot enough to vaporize steel, while just a few billion kilometers away, crimson dwarfs smolder like dying embers, their feeble light a whisper compared to their radiant siblings. This isn't just a family of stars, it's a snapshot of stellar evolution itself, a panorama of cosmic lifetimes playing out in real time. The most striking member is the primary star, HD 93129R, a blue hypergiant so luminous it outshines a million suns. With a surface temperature nearing 50,000 degrees, this stellar titan lives fast and dies young, burning through its nuclear fuel in mere millions of years. Its ultraviolet radiation carves vast cavities in nearby gas clouds, shaping nebulae like a cosmic sculptor. But the real marvel lies in its contrast. Orbiting this blue behemoth is a red dwarf, HD 93129F, a star so cool and dim it's barely visible without amplification. If the hypergiant is a fireworks finale, the dwarf is a match struck in a hurricane, a testament to how vastly stellar destinies can diverge. Between these extremes, the system offers a full stellar spectrum. Two yellow giants, stars midway through their lives, pulse rhythmically as they fuse helium into carbon, their outer atmospheres puffing like bellows. Nearby, a white dwarf, the skeletal remnant of a star that once rivaled the hypergiant in brilliance, cools silently, its heat leaching into space over eons. And then there's the anomaly, a pre-main sequence star, a stellar toddler still gathering mass from a swirling disk of dust, its light flickering as it takes its first gravitational steps. What makes HD 93129 so invaluable to astronomers isn't just its variety, but its intimacy. These stars aren't distant relatives scattered across the galaxy, they're siblings bound by gravity, close enough to influence one another's fates. The hypergiant's fierce winds buffet the red dwarf, stripping away its tenuous atmosphere and leaving a comet-like tail of ionized gas. The white dwarf, meanwhile, siphons material from the yellow giants, occasionally igniting thermonuclear explosions on its surface that outshine the entire system for weeks. The system's crowning irony, its youngest star shouldn't exist here at all. The hypergiant's intense radiation should have vaporized the pre-main sequence star's protoplanetary disk before it could form. Yet against all odds, the fledgling star persists, shielded by a fortuitous alignment with a dense dust lane, a cosmic loophole proving that even in the harshest environments, nature finds a way. For stargazers, HD 93129 is a prism refracting the universe's creativity. Its stars span the full arc of cosmic life, the incendiary birth of blue giants, the steady middle age of yellow suns, the quiet senescence of red dwarfs, and the ghostly afterlife of white dwarfs. To observe this system isn't just to see stars, it's to witness time itself compressed into a single, dazzling frame. Xi Tauri spins through space like a celestial cartwheel, its 6 stars locked in orbits so flat they could balance on the edge of a cosmic knife. Unlike most multi-star systems where orbits tilt at chaotic angles, Xi Tauri's stellar family moves in eerie unison, their paths tracing perfect circles within a single shared plane, a configuration so precise it defies the randomness of typical star formation. Imagine tossing 6 coins onto a table and having them all land perfectly stacked. That's the statistical improbability astronomers face when studying this gravitational marvel. The secret to this cosmic alignment might lie in the system's infancy. Most stars form from turbulent gas clouds that collapse into spinning disks, with planets and siblings often inheriting that disk's flat orientation. But for 6 stars to maintain such impeccable coplanarity over billions of years requires an almost artistic level of gravitational choreography. One leading theory suggests Xi Tauri's progenitor was a single, massive disk of gas so vast and stable that when it fragmented, the resulting stars retained the disk's original spin like synchronized swimmers emerging from a dive. Infrared observations reveal faint traces of a fossilized dust ring encircling the system, a ghostly imprint of that primordial pancake, now stretched thin by eons of stellar winds. Yet the real puzzle isn't just the alignment, it's the stability. Even slight gravitational nudges from passing stars or galactic tides should have warped these orbits over time. Xi Tauri's resilience hints at a self-correcting mechanism where the star's mutual gravity acts like an invisible spring, pulling any strays back into the shared plane. Computer simulations show the outermost stars play a critical role. Their wide, slow orbits create a stabilizing frame that dampens disruptions, much like the weighted rim of a spinning wheel keeps it upright. When one star wobbles, the collective tug of the others effectively pulls the tablecloth beneath it, smoothing out the disturbance before it can escalate. This delicate balance has unexpected consequences. The system's flat geometry means eclipses happen with uncanny frequency. Every few decades, one star passes directly in front of another from our viewpoint, dimming the system's combined light in predictable clockwork intervals. These eclipses aren't just celestial parlor tricks. They've allowed astronomers to measure the stars' sizes with razor precision, revealing subtle distortions caused by tidal forces. One star, Xi Tauri C, is slightly flattened at its poles like a spinning grape, its equator bulging from the relentless pull of its neighbors. Another, Xi Tauri E, shows surface hotspots where violent stellar winds collide, trapped in a perpetual gravitational tug of war. What's most humbling about Xi Tauri's cosmic ballet is how rare such harmony is. For every flat sextuple system, there are thousands of chaotic ones where orbits crisscross like tangled yarn. Some theorists argue this precision couldn't arise naturally, that an unseen super-Earth or even a rogue black hole might lurk in the system's outskirts, shepherding the stars into alignment like an invisible conductor. Others propose a more poetic explanation, that Xi Tauri is a relic from an era when gas disks were colder and calmer, before the turbulence of modern star-forming regions made such perfection impossible. Either way, this spinning stellar wheel reminds us that the universe doesn't just deal in chaos sometimes against all odds. It crafts order so flawless it takes your breath away. Imagine a world where the sun never truly sets, where the sky cycles through hues of gold, crimson, and deep violet, but never fades to black. This isn't a fantasy, it's the eerie reality for any hypothetical planet nestled in the sextuple embrace of the Polaris system. Here, with 6 suns weaving through overlapping orbits, twilight isn't a fleeting moment, it's a permanent state of being. The laws of celestial mechanics ensure that as one star dips below the horizon, another rises to take its place, stitching together an endless sequence of dawns and dusks into a single, unbroken tapestry of light. The mechanics of this eternal glow are as precise as they are breathtaking. Polaris's stars orbit in staggered rhythms, their paths tilted at just the right angles to create a celestial relay race. The innermost pair might circle each other every few days, while the outer stars complete their stately dances over decades. From the surface of a planet, this choreography would unfold as a hypnotic light show. A blazing blue-white star slides toward the horizon, its glare softening as a cooler, amber companion ascends opposite it, casting elongated shadows that never fully merge into darkness. Meanwhile, the 4 remaining suns drift at intermediate heights, some no brighter than Earth's full moon, others gleaming like distant bonfires. But the true marvel isn't just the absence of night, it's the ever-shifting quality of the light. With stars of different temperatures and intensities always in view, the planet's skies would cycle through surreal color palettes. During rare alignments where 2 hot stars dominate, the landscape might bathe in searing silver blue, bleaching colors into monochrome extremes. When a red giant takes center stage, the world could drown in deep carmine, as if submerged in wine. And when all 6 stars scatter across the heavens, their blended light might produce a neutral, pearlescent glow, an uncanny mimicry of Earth's overcast daylight but with no sun behind the clouds. For life, this unending twilight would demand radical adaptation. Plants couldn't rely on predictable day-night cycles to regulate photosynthesis. Instead, they might evolve leaves that pivot dynamically to track the brightest star at any given moment, or spread broad canopies to soak diffuse light from all directions. Animals could develop multi-layered eyelids to filter varying intensities, or perhaps circadian rhythms tied not to darkness but to subtle changes in stellar spectra as different suns take turns dominating the sky. Even timekeeping would require ingenuity. How do you measure a day when the suns refuse to set, or a year when your world's path loops around 6 gravitational anchors? The climate would be equally surreal. Without the cooling respite of true night, temperature swings might depend less on time and more on which stars dominate the sky at a given moment. A passing blue star could scorch the land with ultraviolet fury, only for its departure to plunge the world into a muggy, infrared heavy simmer as a cooler star takes over. Weather patterns would defy terrestrial logic. Storms might form and dissipate based on competing stellar winds, while atmospheric currents twist under conflicting thermal gradients. The very air could stratify into layers, each heated by a different sun's radiation, creating permanent inversion layers where clouds hover like floating islands. Yet the most haunting beauty would come during the system's rarest alignments, when all 6 stars cluster in one quadrant of the sky, casting the planet's opposite side into what passes for darkness here, a dim, eerie gloaming where the faintest stars glow like sapphires in an indigo void. For a few fleeting hours, the land might cool, dew could form, and creatures might emerge to greet the closest thing they have to night, but even this respite would be fleeting. As the stars continue their endless waltz, another sun would soon crest the horizon, banishing the shadows once more, an eternal dawn reborn anew. Polaris's twilight zone isn't just a thought experiment, it's a window into how profoundly alien the universe's rulebook can be. On Earth, we take the rhythm of day and night for granted, a fundamental pulse woven into the fabric of life itself. But here, in this 6-starred realm, nature scraps the rulebook and rewrites it in starlight, proving that even the most basic truths of our existence are nothing more than local customs in a cosmos teeming with alternatives. WR 140 doesn't just survive stellar apocalypses, it laughs at them. This sextuple system, nestled in the constellation Cygnus, bears scars that would have obliterated lesser star families, multiple supernova remnants expanding outward like shrapnel from cosmic grenades, their shockwaves still rippling through interstellar space. Yet against all odds, WR140 stars remain locked in their orbits, as if death itself glanced off them. The system shouldn't exist. According to every conventional model, the explosions that rocked this region should have blasted the stars apart, sending them careening into the void like celestial shrapnel. Instead, they persist, a gravitational phoenix rising again and again from its own ashes. The secret lies in WR140 brutal choreography. At its heart, two Wolf-Rayet stars, cosmic titans on the brink of collapse, orbit each other in a suffocating embrace, their surfaces so close they share a swirling shroud of superheated gas. Every few years, their paths bring them near enough for their stellar winds to collide at relativistic speeds, igniting eruptions so bright they outshine entire galaxies. These outbursts aren't just fireworks, they're pressure valves bleeding off energy that might otherwise destabilize the entire system. When the first supernova detonated here an estimated 300,000 years ago, astronomers expected chaos. Instead, the surviving star's mutual gravity acted like a shock absorber, redistributing the blast's energy so precisely that their orbits merely wobbled before settling back into equilibrium. The smoking gun, a vast spiral-shaped nebula encircling the system, the fossilized debris of that ancient explosion. Infrared telescopes reveal its structure isn't chaotic, as supernova remnants typically are, but eerily symmetrical. It swirls perfectly aligned with the star's current orbits. This suggests the nebula didn't just expand randomly. It was sculpted by the star's ongoing gravitational influence even as the blast wave raced outward. It's as if WR140 didn't just endure the supernova, it tamed it, bending the explosion's fury into a shape that reinforced its own survival. But the real mind-bender came when astronomers found evidence of a second, even older supernova buried in the system's chemical fingerprints. Spectra of the Wolf-Rayet stars show bizarre abundances of isotopes like nickel-60 and titanium-44 elements forged only in supernova's heart. These atoms shouldn't exist on stellar surfaces unless the stars ingested debris from a prior explosion. The implications are staggering. WR140 central duo might be the resurrected cores of stars that already died once, their outer layers blasted away only to reform from the ashes. Imagine a candle that not only survives being dunked in water but uses the moisture to grow taller. That's the level of defiance we're dealing with here. What makes this system a cosmic unicorn is its resilience algorithm. Every close call seems to leave WR140 stronger. When the second supernova erupted, the blast compressed gas in the system's outskirts, triggering new star formation. Two of the system's current members, a pair of hot, young O-type stars, might be these late-born survivors, their genesis catalyzed by destruction. Even the Wolf-Rayet star's deadly winds serve a purpose. They clear space around the system, carving a protective bubble that insulates the inner orbits from galactic turbulence. It's a self-reinforcing cycle where violence begets stability, and catastrophe becomes just another tool in gravity's workshop. For planetary hopefuls, WR140 offers a chilling what-if. Any world forming here would face extinction-level events every few millennia: supernova blasts, gamma-ray bursts, torrents of lethal radiation. Yet if life somehow clung on, it would evolve in a pressure cooker of cosmic proportions. Organisms might develop DNA repair mechanisms that activate during stellar eruptions, or photosynthesis tuned to harness the Wolf-Rayet star's bizarre light spectrum. Their night sky would be a canvas of perpetual rebirth, nebular remnants glowing like ghostly fingerprints, each one a monument to apocalypses their suns outlived. WR140 doesn't just challenge our understanding of stellar survival, it rewrites it. This system proves that chaos and order aren't opposites but partners in an endless dance, where the universe's most violent events can become threads in a grander tapestry of stability. If stars can cheat death this spectacularly, what other impossible feats might the cosmos be hiding? The answer, it seems, is written in supernova scars that twinkle defiantly against the dark. From gravitational ballet performers like HD 98800 to stellar vampires like HD 5980, these 30 discoveries prove sextuple systems aren't just astronomical curiosities, they're cosmic laboratories rewriting the rules of physics. We've seen planets clinging to stability amid six-star chaos, black holes lurking undetected in plain sight, and stars so close they steal each other's atmospheres in real time. These systems defy expectations at every turn. Where else could a supernova fail spectacularly like Eta Carinae, or a pulsar's echoes compose a celestial symphony like Pulsar B 162026's? Each discovery peels back another layer of the universe's inventiveness, proving that gravity's imagination far outstrips our own. What makes these systems truly revolutionary isn't just their strangeness, it's how they force us to rethink fundamentals. Binary stars once seemed exotic. Now we know solar systems can form in the gravitational crossfire of sextuples. Stable orbits weren't supposed to exist in such chaos, yet Kepler 64b dances unscathed. Even time itself bends to their will, as 4U1820-30 proves with its relativistic time warps. These aren't freak occurrences, they're stress tests for astrophysics, revealing where our models crack under pressure. When a single system like WR140 survives multiple supernova or Theta Orionis kidnaps stars from passing clusters, it's nature's way of reminding us the universe plays by its own rules. Yet for all we've uncovered, these systems guard even deeper mysteries. What happens when Algol's perfect clockwork finally winds down? Could life adapt to Polaris's eternal twilight, or does HD 101584's vanished star hint at invisible black holes peppering the galaxy? Every answer spawns new questions, and that's the true magic of astronomy, not just solving puzzles, but discovering how much grander the board really is. So the next time you look up at what seems like a single point of light, remember, it might be six stars whispering secrets across the void, waiting for us to listen. The universe's wildest stories aren't in the textbooks yet. They're out there, hidden in plain sight, daring us to look closer. What do you think we'll find next?